Okay, this is the content of my talk today. So first, I would like just to discuss a little bit how we are going to define efficiency indicators for the system, and then afterwards I'm going to decide to explain how to estimate the cost of the system. So for those who have attended the course of Advanced Analytics is a recap, for the others is something that is new. So first, let's discuss a little bit about efficiency. And typically, at least for mechanical engineers, there is always the question about what is the efficiency in terms of the electrical production. So I'm going to use the first example and to show you that there are indeed several ways of defining the. Take my pointer. So of defining the efficiency of the electrical production. First, what you can say is that the electrical efficiency is defined by the ratio between the electricity you produce and the fuel that you consume. Now, if you supply heat and electricity, then you can perhaps decide that the efficiency is the ratio between the sum of the electricity and the heat divided by the fuel that you consume. Okay? And then you have already a difficulty because you are starting to sum up electricity and heat, okay, which is not always really comfortable for the people. So, but nevertheless, this is what is named the first principle, efficiency. In order to be able to sum in a more smart way, or in a smarter way, the electricity and the heat, so what you can do is to transform the value of the heat into its exergy value, which means that in this case, the sum of the exergy plus the exergy of the electricity and the exergy of the heat is, let's say, measuring the same thing, okay? And then you have to, so you make the sum, and then you divide by the exergy value of the fuel. So the exergy value of the fuel can be found in tables. It's not far from the lower heating value, a little bit higher, but it is expressing the quality of the fuel. Okay, so three types of efficiencies. So the rough one, which is you look at one service and you divide by what you have bought to supply it. The first principle, where there is a risk of summing up things that have not, and that we know that have not the same values, okay? And then the exergy efficiency, which includes the value of the services in terms of the thermodynamic value of the services delivered. There is also another dimension that is important to consider, is the environmental impact, in which you are going to look at the amount that the system is going to release in the environment. And here I'm adding just a term I have, in fact, deduced a term in the case where my system, so this term here, where my system could do a capture of the carbon dioxide, so it will not be directly released in the environment. Okay? Otherwise, the amount of carbon dioxide that will be emitted, and then I have to choose what is the reference, okay? I'm going to make the amount of fuel times the amount of carbon dioxide emissions emitted when the fuel is burned, multiplying the flow by the amount of carbon dioxide makes the amount of carbon dioxide emitted in the stack, from which I'm going to deduce the amount that is captured, so that I get the net emission of the system, that I will divide by the service, so that I will be able to define, in this case, the carbon dioxide emissions per unit of service delivered. Okay, sometimes we can also try to say, okay, why don't we compare two solutions? And this would be the case, for example, when you have when you are making a cogeneration unit. So cogeneration unit is going to produce electricity and heat. And then you can say that if you are producing electricity, you are going to say that the electricity production company do not have to produce this electricity. And therefore, I'm avoiding this company to produce this amount of electricity and to emit the corresponding carbon dioxide emissions. Okay, and in this case, what you are going to consider is that there is a benefit in installing your cogeneration unit. Okay, the same is when I'm replacing the emissions of a boiler. So if I'm doing cogeneration, I'm going to not have to supply the heat with using a boiler. So I can say that I'm avoiding the amount of carbon dioxide emissions that would have been emitted by a boiler. Okay, and then you can show the benefit by comparing, in fact, two situations. The situations where I'm producing the electricity or I'm buying the electricity that I have co-generated that avoids the emissions at the level of the electrical grid. And I have also the avoided emissions because I do not need anymore a boiler, but I'm using my cogeneration unit. In this case, there will be, in fact, two values that are needed because I need to know what is the efficiency of the units that are substituted. Okay, one is the efficiency of the boiler that I will not anymore use because I'm using cogeneration unit, and at the same time the electricity that is on the grid. And there starts the problem, because we have to know what is the mean value of the people who are producing electricity at the time where I'm using this electricity, or when I'm producing this electricity. Okay, so this is named the electrical mix. Okay, and the carbon dioxide content of the electrical mix. This you can find on, there is a website, write it here. Because now the people are trying to do some statistical. You can look on the website ENSOE and you can find the content of the CO2 that is emitted by the electrical grids in Europe, including. Okay. Now, you can also have the values from the past, okay, which allows you to have a good knowledge about what is the mix of power plants that are used to produce electricity now. Okay, which is a combination of nuclear power plants, coal power plants, combined cycles, and PV, and wind, and hydro. Okay, at a given time. And this can be important, especially when we look at what is happening in the summer or in the winter. In the summer, there is a risk that, or the chance, that the carbon dioxide emissions related to the electricity will be quite low, while in the winter, when the coal power plants are operated in Germany, the load of the carbon dioxide might be quite high. Okay? So this is for the environmental impact. I have also made an exercise, and it is not published, so you have to take notes of it, of what is then the method that you will use in your case. In your case, you are supplying heat and electricity to the buildings. So it means that you will have to make the the sum, if you want to have the first principle efficiency, then you will have to make the sum of the heat load and the electricity that is supplied to each of the building, then you make the sum. You have to make an integral of it, okay? And you will have to consider that there is an additional service if you are using cogeneration. So there is a gas turbine here, so it means that if you choose to use a cogeneration unit, then one of the services that you will supply in addition to the needs of the building will be the exported electricity that you can have at a given time. So those are the services that you supply, and on the other hand, you have the resources that you are going to use, which is the fuel, and you can have different types of fuels. That's why I have made a sum that you multiply by the lower heating value, plus the electricity that you import. Okay? And then you will have a problem, probably, especially when you are using the energy from the environment, because you can see that the heat that I'm harvesting in the environment is not accounted. Okay, so it might happen that the efficiency is bigger than 1. Okay? On the other hand, this is the reason why we are going to introduce another type of efficiency, which is the exergy efficiency, in which, so you can see that I mostly have taken this formula there, but now I have added the exergy value, which is here, of the heat, which is the value in terms of electricity of the service that is delivered, considering the temperature at which I have to supply the heat, which is the one that you have calculated. Okay? To which I'm going to add the electricity that I'm consuming plus the electricity that I'm going to export. And in this case, I can divide this by the exergy that I'm consuming. Okay? And then I will have, I do not have the problem of the heat from the environment, because the heat from the environment has 0 exergy value. Okay? And in this case, I'm sure that this one, due to the energy balance, will always be lower than 1. So I'll let you take notes. I'm summarizing again. So this is, I will post it afterwards, but it's good that you write it. Okay? This is the exergy value of the heat that I'm supplying. This is the electricity consumed in the building. This is the exergy that I'm exporting. And this is what I'm consuming, which is the exergy value of the fuels plus the electricity that I'm importing. Okay? Yeah.
What is the factor K?
So the K here is the exergy value of the fuel. So it's similar to the lower heating value, so it's equivalent to a calorific value of a fuel. Okay? But it is expressed in terms of exergy. The K is named, it's a co-enthalpy. It includes, in fact, 2 terms, the heating value and the exergy content. So, sorry, the entropy content of the fuel. Typically, the K is the lower heating value multiplied by 1.04 in conventional fuels. And the explanation is that the lower heating value is supposed not to condense the water that is produced by the combustion. Okay. While if you cool down all the flows up to the ambient conditions, then you will condense part of the water that is produced by the combustion, and this gives you a higher, a small amount of more energy than the lower heating value to define the exergy content of the fuel. Okay. This can be found in tables. Okay? So now, when you will have to calculate the environmental impact, then you will have to calculate, to make again an integral from a given time to an nth time, and then you will have to make the amount of carbon dioxide emissions that the unit is going to produce, which is the amount of the carbon dioxide emissions for the different fuels that you are going to use, that you will multiply by the flow, and then you make the integral. Okay? And you have to know what are the emissions associated to the fuel. And then the same for the electricity that you consume. You have to know what is the CO2 content of the electricity that is supplied to you. I'm defining it like this because it means that if I have losses on the grid, I have to produce more electricity than the amount that arrives to you. And then afterwards, you have to account for the emissions that you are doing when you are producing the electricity. So perhaps I would have even to add a dependence with the time there, because we know that there is more carbon dioxide in the electricity production in the winter than in the summer. Okay. The specific emissions are a little bit more complicated to define, okay? Because yeah, I would be happy to have some sort of a CO2 emissions per kilojoule, okay? But then I will have the difficulty of summing up heat and electricity. So it means that this one, I would not recommend to use it. The emissions per year is perhaps a better indicator. Okay, so those are efficiencies, okay, or flows to the environment. At the same time, we will have to consider the amount of the operating cost. You have seen that the operating cost is an integral in reality. So here I'm just defining the cost that we will have in a certain period. So you will define typical periods. So in each of the period, you will have to make the calculation of the cost. So the formula is quite, might appear to be complex. The reality, it's not so complicated. So what you do is that you sum up all the resources that you are going to consume, because you pay for each of the resources that you have. So you pay for electricity, you pay for fuel. You will have to deduce from what you pay what you sell. So, for example, if I'm exporting electricity, then I will receive a premium when I'm exporting the electricity. But if I have installed, for example, biomethane production and I want to export natural gas, because I'm producing gas and nobody needs the gas at a certain time of the year, then I will have an income from selling the gas. Okay? So it means that you make around your system the flows that are entering, the flows that are leaving. You will see that I'm going to add, in addition to this, the emissions that can come with a penalty, so I have to pay if I'm releasing some emissions. Okay, and I will have to take, therefore, all the flows that I have in each of the periods, multiply by the value that each of the flow has in each of the periods, to have the cost in a given period, that I will multiply by the number of times this period is going to appear, or this hour, or this day is going to appear, to have how much it costs for this period, and then I will make the sum over the whole lifetime of my equipments to have the operating cost of the system. And this will define the first part of the question. The second part of the question is that I would like to have the total cost, which means that I will have also to look at the investment of related to, and the cost of the investment. So what is the mechanism is that by writing mass and energy balances, I will be able to know what are all the flows. Knowing the flows, meaning that I know the temperatures, meaning that I know the pressures, okay, I will be able to, by applying models of sizing equipments, like the one that I have shown for the heat exchangers, I will be able to calculate the sizes of the different equipment. And once I will have the size, then I'm going to calculate the investment. So sizing the units is in fact related to the knowledge that engineers have of the principle of the energy conversion in the different devices. Okay, so heat transfer for heat exchangers, compression for compressors, and typically you can have handbooks that are going to tell you, okay, if you have to go from this pressure to this pressure with this type of compressor, then you have to size it in this way. Okay. Typically, those are encyclopedia. So, for example, you have the mechanical engineering handbook, you have the chemical engineering handbooks, and they are telling you how to do the sizing, and they give you, in fact, rules that are that have to be applied by engineers to size equipment. Okay, those are big books, and at the end, it translates into a list of equations that is a function of some parameters that are coming from the experience. So the values of the parameters are values that are given to you by experienced engineers that say, okay, if you are in this situation, I would use those parameters. Okay? And then you take those parameters and then you are able to define the size. So that's why these sizing procedures are typically heuristic, okay, coming from the experience of all the engineers that have shared their experience. It is also typically sequential because I can take each one of the elements in the system and make a specific calculation for it. Specific calculation for the pipes, specific calculations for the heat exchangers, for the compressors, etc. Okay? So it means that now I will be able to know what is the size, and then afterwards I will have to define, and you can see that the size depends on the conditions and the parameters, or the type of the unit. Then I will have to have something that is allowing me to calculate what is the investment that is associated to this size. So how much do I have to pay if the heat exchanger is a double pipe heat exchanger with a given area? Okay, and this is what I'm going to explain you after the break. Do you have questions? No questions? Okay, then let's do the break, and I'm going to start in 15 minutes. So the things that I'm presenting on my iPad, I'm going to download it, but after the course, okay, so that you can have the final version. But I would like to encourage you to take notes, so it's also good to write things, right? Now for the second part, I'm going to make the calculation, discuss about how we estimate the purchase cost of a system that is going to have a given size and have a given type. And typically there are two dimensions to it. On the one hand is you have to buy the equipment so that they are delivered at the entrance of your plant, and then you have to connect them. Okay, and so there are two different dimensions: the purchase of the equipment and then the installation that includes piping, control systems, the foundations, all the safety aspects that needs to be considered. Okay. So when you have to estimate investment, what you can do, of course, is to go towards a very detailed design. So if you want to buy a heat exchanger, of course, you can calculate how many tubes you have to produce, what will be the time needed to assemble all the tubes to make the shell, how to add all the sensors, and then there will be a cost related to the engineering of this. But the more precise you want to be, the higher will be the time that is needed to make the cost estimation. And the problem is that we would like to have an estimation that is going to be fast enough, okay, so that we can take the decisions: do we buy this heat exchanger or not? Because I don't want you to make a very nice detailed design with all the tubes and the shells, etc., of a heat exchanger if okay, sorry. I don't know why Adobe is asking me to update things. So, so the question is, how can I make the estimation of the investment without having to spend too much time in doing the design, the detailed design? Okay, and the answer is that we can use the experience of people. Okay, so that we can go very fast in making the calculation of the estimation. But of course, I will not be precise, so I have to make a compromise between the precision of the estimation and the time I'm going to spend to obtain it. Okay. So let's consider that we will accept of not being really precise but fast. And in this case, there are two tricks that can be used. The first one is that you can see, for example, that you need a heat pump. So what you do is that you look at what was the price of the previous heat pump that you have bought in the past. Okay? And in this case, so you will realize that perhaps that the heat pump has not the same size as the one that you expect. Okay? So it means that you need to have something which is a scaling factor. Okay? The scaling factor is typically not linear. So it means that if I have a reference size here and a reference cost, then the cost of the system will be sized, so it means that it will be proportional to the size, but not linearly dependent. So we know that the bigger the systems are, the less per unit you will have to pay. Okay, this is a typical rule mainly from the mechanical and the chemical industry that says that if you have, for example, to buy a very big gas turbine, per unit of kilowatt, the gas turbine will be cheaper than a very small one, okay? Especially because the time to make the engineering will be the same for a very big one or a very small one. Okay, so it means that at the level of the cost, it will cost more to make a small one than to make a big one per unit of installed power. Okay, so it means that the difference, the scaling factor will be not equal to 1. And I give you the value, so it's not written on the slides, but you have to take the value between 0.6 and 0.8. Okay? From my experience. So if you do not have any idea of what is the exponent for a given equipment, take 0.6. And then the second dimension is that the time at which you have obtained the reference costs. If I'm looking at the heat pump of EPFL, it has been bought 50 years ago. Okay, you can find the bill and you can say, okay, a heat pump will cost so much, but it will be in Swiss francs from 50 years ago. So it means that we have to translate this into Swiss francs of today. And for doing this, then we use a system which is an indexing system that is based on the observation of what is the value of the money for buying equipments with time. Okay, and those values can be found in journals like the chemical engineering journal, that is going to report each month the value of the index of a given equipment. So this is a trick that you can use if you have and if you know already one equipment. Okay? Now you have to be, you can be happy because there are a lot of people that have looked at their shelves and then identified that they have a lot of costs available and they have shared all those costs and they have developed formulas for typical equipments that allows you to know what is the cost or to estimate the cost of different equipment. Okay, so this is a statistical approach. So what is in the formula here is the cost, the purchase cost is so always this index mechanism times, and then you can see here is you have 10. And then the exponent is something which is a linear or polynomial function. So what is the reason for using this polynomial function with a 10 exponent? Is in fact it's because in the log domain, so if I'm looking at the logarithm of the cost and the logarithm of the size, then the curve appears to be like a line. Okay? Although I'm observing a market, so it means that the cost that I will see is the result of the negotiations that the supplier offered to the customers. Okay? But in the log domain, it means in the order of magnitude domain, then we see something which is like a linear function. Okay? And that's why the statistical analysis follow this 10 exponent here rule with those three elements here. So what you can see is that if K3 is equal to 0, so it means that here you have a line, then T2K to the 10 to K1 is indeed CP-ref, and 10 to K2 is the gamma. Okay? So the two formula are exactly the same. And they express that there is a trend in the order of magnitude, okay? That translates into a very complex nonlinear function. So to give you more information, I'm going to give you some examples. So this is something that my student has made, observing the market of the compressors in Switzerland. Okay, so he has collected a lot of information about, so each point is one compressor that he has received, okay? And you can see that there are a lot of compressors that were available, okay? He has obtained the cost and has plotted as a function of the flow rate. In this case, we decided to use as a sizing dimension the suction flow rate because it defines the volume that will be needed at the entrance of the compressor, so where we have the biggest or the lowest density. Okay? And then what he has done is that he has made a very nice function like this one, where we can see that the cost of the compressor is a function of the volume. The volumic flow is a function of the pressure at the inlet, pressure at the suction at the distribution pressure. And he's giving us ranges in which the function is valid. The ranges are also very important because this is expressing the zones in which the function has been calibrated. Okay, so very important to use, to be aware that it's not only a question of having a very nice mathematical formula, but all those parameters that are in the formula needs to be associated to a reality, right? And the association to the reality is that we have collected data with those type of limits, and therefore the function is only valid in those elements. But you can see as well, those ranges, sorry. You can see as well that you have different types of technologies that appears to be in different ranges as well, okay? Which also gives you an indication of which kind of compressor to buy, knowing the pressures under which you are going to operate and the flows that needs to be processed, okay? So this was a big job. You can see that the order of magnitude of the error is up to 15%. Okay, we have to accept this. You can see that there is a distraction here, and especially because we are talking about logarithmic scales. Okay, but nevertheless, so it fits quite well, and we can use this within a 20% error to estimate the cost of the compressor. Okay, and we have the same for the heat exchangers. Okay, we have the same for the pumps. It means that now you have nice formula that allows you to estimate the cost of the main equipment that we need. Okay? So use those formulas and you can already estimate what will be the cost of the heating system here. Okay? I give you also the cost index. So the index are published every year. Okay, I have here up to 2005, but they are published every year. There is a reference year that has been selected as being this one in 1957, and then each year it is updated. And if you go into the Chemical Engineering Journal, for example, you have even an index for the different types of equipment that you have in the system. And it might happen that some equipments will have different evolutions than others. So for example, let's take the fuel cells, for example. The fuel cells are going to be cheaper and cheaper and cheaper because they are emerging technologies. The same for the PV panels. So if I would have used the PV panels in 1957, it was not existing at all. Okay? So it might happen that the index is going down for some of the equipment. Okay? And this is made by people who are observing the market. Okay? So use those information, and you can always go to the journals like the Chemical Engineering Journal to get this cost index. Okay? In addition, some people have proposed also adaptation of the formula to account for the fact that you would perhaps need a special material in a compressor. Okay, if the fluid that you have to compress is corrosive, you will have to change the material, and therefore you will have to pay an additional amount for the material. The same for the pressure. So if the pressure is changing, then you know that just to withhold the pressure difference, you have to change the thickness of the tubes. Okay. Therefore, there will be a factor that will be related to the operating pressure at which you operate. Okay. So this is what is named the bare module factor, which includes all what is needed in addition to the typical to the estimated cost that you have in the formula. Okay, and which allows you then to have, by having the bare module factor, to have the estimation on how much the equipments, when they are assembled, will be costing. I give you here some tables that are coming from this book here, which is in fact taking the information from another book. So what is important to always note is this. What is the date at which the the book has been published, because it's the date at which the information was available. It means it's the date at which all the values that are in all the different, so the K1, K2, K3 for the purchase cost, plus the pressure influence, plus the material, not the material, but the installation part here. And something which is also very important, you have it for different types of heat exchangers, for example here, is the minimum value and the maximum value, so the ranges of validity of the formula. Okay? Very important, because it also indicates you which are the sizes that you can find on the market. So if you need 100 square meters of a double pipe heat exchanger, then you know that you have to buy 10 units. Okay, because you will not be able to buy a double pipe of 100 square meters. Okay? And of course, as soon as you have those information, so don't forget the value of the reference index of the data that you are reading there. Okay, and then this is the material factor. So some people have also developed more sophisticated equations, okay, that accounts for flows, that accounts for pressure difference, and you can have very complex formula. So be just careful on what are the references, what is the date, and be sure that it is related to real values from market. Okay, I give you just one story on this. There were very nice correlations published by people in the mechanical engineering community to optimize energy systems. Okay, all those correlations were used by and cited by all my colleagues, and then one day I discussed with the person who has proposed the problem formulation and proposed those correlations, and he said, yes, I did those correlations just to have a very nice problem formulation. Okay, so which means that the values that were used were not real values from markets. Okay, so you have just to be careful about this. Okay. So when I have the bare module factor and the purchase cost, then I can calculate the bare module cost, which is the cost that the unit will have when it is connected to the system. Okay, and typically there is a factor 4 between the cost that you pay to have the unit delivered at the entrance of your plant and to have the unit connected to the and operated in the system. Okay, so it means that and this is quite important, because then sometimes you see, oh, it's quite cheap, but when you have to install all what is needed, so the foundations, have all the pipes coming to your heat exchangers, and then the control system, then you have a multiplication factor which is of the order of 4. Okay, so order of magnitude, which is important to know. So now it remains one small problem, which is the fact that I'm going to buy a heat exchanger. So I will have the bare module cost here, which will be expressed in euro or in Swiss franc. Okay, that I would like to be able to compare with the operating cost that I will have typically in Swiss franc per year. Which means that I have to be able to also compare the money that I have to spend to buy an equipment today, okay, with the money that I will spend over the year lifetime of my equipment, which will change with time and with the value. Okay, so it means that I have to account for this time dependence of the money. And in order to do this, then what we are going to do is that we are going to, what we say, annualize the cost. And to annualize the cost, what does it mean? It means that, let's assume that I'm investing today. a certain amount of money that I'm putting in a bank with an interest rate of I for a certain number of years, then I know that after n years, I will have the I star here, which is the amount of money that I have, that I would have obtained if I'm placing this amount of money in the bank at a given interest rate. Now, instead of being in a bank, I can also be a stakeholder of a company. Okay, so it means that now I'm going to invest in a company, and I hope to obtain a certain return from this investment that I will express into an interest rate. Okay, which means that if I'm a financial person, I'm going to give a certain amount of money as capital, and I will expect a certain interest rate that I would like to obtain, okay, over a certain number of years, which is the n years, and the n is the number of years during which I will not have my money back because the money is placed in an equipment. Okay? That means that I can translate, therefore, the mechanism of putting money in a bank into investing in an equipment. And this is the amount that I'm expecting out of this equipment. That is associated, to the investment. So this is what I'm expecting out of my investment. So how do I make the money out of it? I'm making an investment for a given purpose, which is going to give me a certain profit each year. Okay, so for example, I'm investing in a heat pump in EPFL, and EPFL is going to pay me each year a certain amount of money to be heated. Okay, and each year they will give me a certain amount of money, and as soon as they give me the money back, I'm placing this money in the bank, and it is going to make some interest. So meaning that at the end of the n years, the profit will be this one. Now, what I can do now is to say, okay, can I calculate the investment that corresponds to the profit that I'm doing each year? And the answer is yes, because I can always calculate the benefit that would give the same value as the investment in this formula. Okay? So now I'm obtaining what is named the net present value of an annual income that is transformed into an investment that I'm doing today, in money today. Okay? And this gives you, this is given by this formula here. Okay? So it's the value in the investment of a profit that I'm doing every year with an interest rate of and over the lifetime of the equipment n. And I can do the same by calculating what is the profit or the equivalent annual income of a given amount of money that I'm placing in my equipment. And in this case, I'm obtaining here the annual expenditure, which is expressed as the income that I should receive if I'm investing the big A, the big I here, amount with a given interest rate and for a certain number of years. So this is the expected amount of money that I should receive to compensate my investment. Okay? Which then allows me to calculate what is the net present value of my system by comparing the investment that I'm doing with the equivalent income expressed in Swiss francs of today, or the annualized cost, which is the profit that I'm doing minus the amount that I have to pay to reimburse my investment. And in both cases, so the net present value has to be bigger than 0, and the annualized cost has to be bigger than 0 to justify the fact that the investment makes sense. Okay? Although if it is negative, then it means that my income will be lower than the value of the investment. Of course, this depends on the interest rate. So if someone is asking, he wants to take big risk, then he's going to tell you, okay, I want to have a big. No, if someone estimates that there is a big risk, then it will ask for a big interest rate. If it estimates that it's not a big risk, then they will give you a smaller value for the interest rate, and it will be affected here. So what I wanted to show with this figure here, so I have plotted here the interest rate, and here I have plotted the number of years during which I will reimburse the investment. So I will spread the investment. Okay, and this tau here, which is investment divided by the number of years, is in fact the expression of the which is given here. So it depends on the interest rate and the number of years on which you will operate the system. So it's like an amortization of the investment, except that it is not over the whole lifetime, so the number of years on which you will operate, but you have to pay for the interest rate, which means that it is going to shorten the time. So for example, here, I was expecting in this blue line here to operate my system in 15 years, and what you can see is that if you expect to have 6% of interest rate, then instead of dividing by 15, you have to divide by around 10. Okay, and what you can see as well is that the highest is the interest rate. So this is the value, for example, for the energy company, the utility company, so around 8%, or I expect to have 8%. Okay, but you can see that if the lifetime is 15 years, then you have to divide the investment by, let's say, 8.5, more or less. Okay? So the more you ask for the interest rate, the more important the investment will be, because the value is smaller. Okay? And if I'm doing this, then I will be able to express the total cost. The total cost will be the comparison of the operating cost over all the projects that I have considered, plus the capex of the investment that I have estimated, and I have shown you how to do it today, that I will have to annualize by this by the annualization factor. And now I have the total cost expressed in Swiss francs of today. Okay? With one big uncertainty, which is related to the operating cost, because we consider that in the 25 coming years during which we are going to use the equipment, we assume that the energy cost will be the same as today. If the energy cost is going to, or the price of energy is going to change, then this formula is officially not valid anymore. Okay? But nevertheless, it allows me to have an estimation of what will be the total cost of the system, right? And having the total cost of the system allows me then to compare solutions, because now I have investment and operating cost. So it means that sometimes cheaper solutions with low efficiencies will lead to high operating cost but low investment, and more efficient solution will need more investment because you are going to refurbish the buildings, you are going to buy more heat pumps in the system. So more investment but lower operating cost because you are going to buy less electricity. Okay, especially if you have the electricity coming from the roofs. Okay? And the last dimension is that normally this function has to be also improved by adding the contribution to the cost of the environment. I'm emitting carbon dioxide, so it means that someone will have to pay for mitigating the carbon dioxide. Okay, I'm emitting NOx. If I'm emitting NOx, there will be an impact, and typically the people say, okay, you have to pay for it. Okay, so it means that I will have to add to the operating cost a cost that is related to the different flows of emissions that I will have in the different periods, times so the flow of the periods and the duration of the periods, and the tax that is associated to each of the emissions. And to this, typically, in addition to the fact that I will have to pay for it, sometimes I will have constraints. They will tell me, okay, you are not allowed to emit more than so much amount of NOx or so much amount of sulfur. And sometimes the value is 0, so it means that it eliminates solutions because it's not anymore possible to use it. Okay? So those are constraints that are added to the system and that represents the environmental cost. And if I want to be fair, I have also to add to this the life cycle impact. What does it mean? It means that when I'm using natural gas, I'm going to emit carbon dioxide because I'm burning natural gas. But someone had to extract the carbon dioxide at the well, had to compress it, to clean it, to transport it, to distribute it to my place, and all those steps consume as well energy. And as they consume energy, they are going to also do some emissions. So it means that officially I have not only to consider the emissions that I'm doing locally, but the one that have been induced by the fact that I need the fuel to be delivered to my place. Okay? And for natural gas, it's around 20% of the emissions are emitted before burning the natural gas. Okay? It's all the emissions that are due to the fact that I have to transport the natural gas to your place. The same for oil, around 30%. And if we go to shale gas, for example, it's half of the emissions are done when the gas is delivered to your place. So it can be very important. And at the same time, I have also to consider that if I have to buy equipment, so for example, we are going to buy PV panels on the roofs, I have to account for the fact that to produce the PV panel, I have spent energy. So it means that I have induced emissions. Okay? So it means that when I'm doing the evaluation, I should be fair to the rest of the world and to account for my contributions related to the investment. And in addition to this, I should also consider that when the solar panel will be dead, I will have to dismantle it. And perhaps it will cost energy to dismantle it. Okay? And think about a nuclear power plant. Okay? In fact, when you have to dismantle a nuclear power plant, you pay even more than the cost of producing it. Okay? And you will have to take care about the waste for a long time. So it means that it has a cost in addition to have an environmental impact. Okay? So it means that I have to consider not only what is embedded in the investment, but also what is induced by the fact that I will have to dismantle my equipment. Okay? Questions about this? If not, then you will have to apply it, because it means that what we have seen today is that with a systematic approach, you can now estimate not only what will be the benefit of integrating an option on another one in terms of operating cost, but you will have also the possibility and the duty of estimating what is the investment associated to the options that you are going to evaluate. You will compare the savings in an efficiency and the investment that is needed to reach savings, okay? And since now you are even not allowed to ignore anymore the fact that as soon as you buy something, and as soon as you have to construct something, as soon as you need to receive something from outside, and as soon as you emit something in the environment, there is an associated cost that should normally be accounted into into the cost of the whole system. Okay, you will see that one of the difficulties is to collect data. Okay, and the additional difficulty will be for you to integrate those data into models. Okay, because the first thing that you will see is that as soon as you decide to buy one heat exchanger at a given place, you will not be sure that the temperature difference of the heat exchanger is the right one. Perhaps I could increase it a little bit or reduce it a little bit. And if you forget to write the formula, and that you write everything on a sheet of paper, then you will be frustrated. Okay, so that's why we develop models. Okay, with what I have shown today is that it's easy to make sums. It's easy to apply mathematical formula. And there are a lot of mathematical formula that are available and made available to you by all your colleagues from the past. Okay, so don't forget the work that has been done, include everything in models, and so you will be able to evaluate in the right way solutions. Okay? Right. So, this is the end for today. Next week, I have been asked to participate to a conference in the Federal Office of Energy. I'm not sure about the time at which the conference will start, but there are some chances that I will not be able to come to teach next week. However, the next week is the presentation week, so you have to present the results that you have already obtained for the identification of the buildings and the typical days that you have to select. Alessio will be, and the assistant will be there to listen to your presentations. They will make a critique on your presentations so that you will receive a feedback about what you have done. And afterwards, there will be a consolidation, because we would like to be able to calculate the whole campus. Each one has some buildings, so we have to assemble all the buildings, and we have to be sure that everyone has made the consistent calculations. Okay, so it means that at the same time as the assistants are going to give you a feedback, it's important that everyone here in the room is criticizing or is sure that the values that are produced by the other are correct. Okay? It means that this exercise will be also for you a way to learn how to discuss with your colleagues. Okay? When you will have to do a job like the one that we are asking you to do here, you will not most likely be alone to solve the problem. Okay? And you cannot be polite, in fact. This is something which is very important. At the end, you will need the results of the other. But you have to be convinced of the results of the other. So it means that if something is not clear, or if an assumption is not clear, you have to tell it. You have to be, and you have to make a negotiation. Okay? Everyone can make an error. Everyone can make a wrong assumption. If you have to negotiate to make the good assumption, you have to do it. Okay? Because at the end, everyone is signing the final report. Huh? That means that you cannot, in front of your boss, say, but this is my colleague that has decided it, and he has made silly things. Okay? No, you are all signing the final report, so it means that you have to be convinced about all the values that you will use for the future. Okay? It means also that if you are presenting, it's not a problem of being offended. Okay? If people are telling you, I do not understand this, or can you explain what are the assumptions that you have made, because I want to be convinced. Okay? So please play the game. That's the best place to learn how to play this game. It's much easier today because there is no risk of being fired if you have done something wrong. Okay? So challenge yourself in the group first, and then afterwards challenge yourself in the class. Okay? And the assistant will help you doing this. Okay? Right.